how do we find out the domain of a function? That is what is going to be discussed in this lecture. So I'm sure all of you people remember that a function is such a relation where all the elements of the domain set get linked with some of the other elements from the codomain set. The linked elements are known as range. Further, the relation can be such that it is 1 to 1 or it can be many to 1, right? Then it is a function. But if you have a function, then the codomain set can be larger than the range set, or in other words, there can be some elements which can be left out in the second set, that is the y set or the codomain set, right? So all of this we've already discussed. Now at this time we actually have to discuss how is it that for a given function we can find out the domain. Obviously there are times when we are very fortunate and probably we've been given certain sets which are in the roster method or probably in the tabulation method, where the value of the domain is given to us like say 1, 2, 3, and all of this is going to happen up to 7. And if this is not there, probably you will have to find out the value of the domain with respect to a replacement set, right? That is just like the set of natural numbers or real numbers or anything like that. For that matter, we actually have to consider certain conditions under which a function will actually be valid to be having that value as a domain. For that matter, let us quickly consider a case where we have say some function f of x which say can be given by x square plus 7x plus 17, and let us say this is divided by x minus 3, right? Now as you see that this is a rational function, that means there is some algebraic expression which is there in the numerator, there is some algebraic expression which is there in the denominator, and it is very much possible that you will get the answers to be in fraction. So there is no problem, because normally we consider that whenever we talk about a function, it is from real numbers to real numbers. That means the domain as well as the range both are from the set of real numbers, so no problem. But we'll have to find out such sort of a case where actually the value of x will not be possible. For that matter, if we consider the value of x to be say 1, then obviously there's not going to be any problem, because the numerator will come to some value and the denominator will come to minus 2, which is not defunct as such. It will come to be a fractional value, but even then it will be a valid fraction. But what if you get the value of x kept to be 1, 2, no problem, but the moment you keep it to be 3, obviously here what will happen is the denominator is going to become equal to 0. As such, the value of the function will come to an absurd value. For that matter, I'm sure you people must be knowing that if say you have a number like 14 upon 0, then such sort of number is undefined and it is said to be absurd, and then we don't consider that value of domain, right? So such values of domain, when avoided, right, will actually give you the domain which is probably from the set of some specific replacement set that you've been given in the question, right? So this is all that we're going to do in this part of the study. Now let us quickly begin by looking up a question, then I'm sure you'll be able to understand this much more. Okay, so for this, now I have kept for you people a question. Now I like you people to initially give this question a try. I'll give you some 10 seconds for trial, and after which, children, we're going to discuss the question. Make sure that you're seated at a place where there is no disturbance, you don't have any electronic gadgets, and make sure that you are sitting on a table and chair, sitting straight, and that is the way how you can concentrate the best. Okay, now think that you people have given it a good try. If you've not, please pause the lecture and give it a longer try in accordance with what all you know, right? If there is something that you've been able to do, then obviously that will be a positive thing and you can pat yourself for that. If you haven't understood, obviously I'm here to explain and I'll ensure that everything is very well understood. rather now we move ahead with the sum, and as you see that here in the question we've been given this, that there is actually a function f of x which has been given to us, that is x square minus x plus 1, which is divided by x square plus x plus 1, and in this case we've got to find out the domain of the function. Now, like I told you, for such sort of a function, the first thing that we're going to try and do is we're going to try and find out one such value, or probably a group of such values for which the denominator can become equal to 0, and that is what you can do in a rational function. That is the only non-probability of values of domain. Under all other conditions, this function will be valid. For that matter, we actually will have to try and find out when x square plus x plus 1 is equal to 0, right? So we will say that for denominator to be 0, we should have x square plus x plus 1, which should be equal to 0, right? Now children, we will try and actually see whether this is 0, or probably this is some positive number, or this is some negative number. Thus, if you talk about trying to make a perfect square of this, we have already an a square which is present, that is x whole square. Now we should get to the second term, which should be of the form of 2ab. As such, it should be 2 times of a we already know as x, and if we keep the value of b to be 1 upon 2, then what will happen is 2 will get cancelled, and we will actually get a 2ab term, which is x, right? Next, now what we do is, as we have here the value of b, which has been found out to be how much? We have found it out to be 1 upon 2, right? And a already here is x. As such, now we will try and write the b square term, which then is going to become equal to 1 upon 2 whole square, right? And as here we have written this 1 upon 2 whole square out of the way, it was not there, right? As such, we also require to subtract it and make it minus 1 upon 2 whole square, so that both of these things get cancelled, and we have what we originally had, that is x square plus x with us. Now remember children, there is also another plus 1 waiting for us, so we will write that here, right? And we'll put all of this to be equal to 0. Now children, here you get to see that there is something which is very interesting, that is the first 3 terms actually are forming a perfect square, and they are forming a perfect square of what? X plus 1 upon 2, right? And we will square this. As such, we'll be able to get to this trinomial. Now except that we have minus 1 upon 4, that is minus 1 upon 2 whole square, and to that is added 1, and the sum of all of these 3 is equal to 0. Now as the last 2 are constants, we can deal with it and we can find out a value, so that will then become equal to x plus 1 upon 2 whole square, right? To which is going to be added 3 upon 4, as we can find out the LCM, which becomes 4, and then from 4 if we subtract 1, that's going to become 3, and thus you see that we have x plus 1 upon 2 whole square plus 3 upon 4, right, which is equal to 0, is what we will try and check. But if, say children, you talk about this x plus 1 upon 2, whatever value of x you keep, you will always find that this is going to come out to be a positive number, except you keeping the value of x to be minus 1 upon 2, right? So as such, this value will either be positive or it can become equal to 0. Now to that is going to be added, either this is going to be positive or it is going to be 0. Where is it going to be 0? It is going to be 0 when we take the value of x to be minus 1 upon 2, right? Now for the children, to this is added for sure a positive number, that is plus 3 upon 4, which obviously on calculating decimals will become 0.75, right? So to this is added another positive number, right, which we will write here is another positive number. So as such, even if the first term becomes equal to 0, even then we'll be left out with this positive number. As such, their sum will become equal to 3 upon 4, which indeed is going to become a positive number, right? And as such children, this can never be equal to 0, right? And thus we have this denominator which can never be equal to 0. As such, any value of x you keep, that is going to be perfect for finding out the value of this function. As such, we will not get any defunct value of f of x for any value of x. And thus, when we want to finally write what our answer is, we can now write thus that our answer is going to be that the domain of the function, right, is going to be an element of real numbers, right? Because there is no real number which is causing it a problem. Now, why do we write it like this? That is because, do remember that whenever we talk about a function, it is actually, we have any function, say f, and f is a function from real numbers to real numbers. That means we consider the domain to be from the set of real numbers, right, from where we choose the independent variable, and R represents the range, right, and that also is the set of real numbers. Okay, so here children, this is how you find out the domain of a function, and this is going to be applicable in most of the sums. Obviously, with different sums there will be slight change of technique, which in times to come I will be telling you. So here I will quickly discuss as to how to find out the domain of a function. Now, the first thing children you've got to remember is, whenever there is a function which is an algebraic function but it has some denominator which is again another algebraic expression, it is a rational expression of x, and for such an expression you got to see to it that the denominator should not become equal to 0, because if it does become equal to 0, then the denominator being 0, the value is going to be defunct, right, and absurd. As such, you will try and avoid it, and thus we've just got to try and check that the denominator, whether it's actually becoming equal to 0 for any value of x, right, and that then is going to be removed from the replacement set. If you've been given that the function is defined on the set of real numbers, then from the set of real numbers that value is going to be subtracted. If you've been given that the function is defined on the set of integers, from the set of integers that value is to be subtracted. Okay, next now children, we talk about the denominator, which is quintessential, and we will try and check that whether this is 0 or not. For that matter, let us consider it to be 0. So we can say that x squared plus x plus 1 initially is to be equal to 0, and we will try and prove this by contradiction, that is showing that this is actually not equal to 0. So for the children, as this is a quadratic expression, we will try and make this to be a perfect square. As such, the first term is already a perfect square. It is just like a square, so it can be written as x whole square. Then for the next term, which is the linear term, we should have it like 2ab, right, as we are trying to plan and get a plus b whole square, right. Thus it should be 2, which should be there, a, which we've already found out to be x, and the value of b should be 1 upon 2, so that 2 and 2 get cancelled and we get x, which is what is required here as the linear term, right. And thus we've got the value of b to be 1 upon 2, and thus we should be having a plus b square, and when we write it, we have plus 1 upon 2 whole square. And since we have written this extra, we also require to subtract it, so that both of these getting cancelled, we get the old expression back. Now remember, there was also a plus 1 which was added to this, and that we will add here. And further, thus you get to see that this trinomial, which is at the beginning of all of these algebraic expressions, right, is the perfect square of x plus 1 upon 2, right. And from that we have subtracted 1 upon 4, which is 1 upon 2 whole square, and to that is added plus 1. Now the sum of both of these becomes equal to plus 3 upon 4, which actually is a positive number, right, to which even if 0 is added, it will remain to be positive. And to the minimum, you can have x plus 1 upon 2 whole square to be 0 when you have the value of x to be minus 1 upon 2. You can't make this to be a negative number, because howsoever large a negative number you keep, that is going to get added to 1 upon 2, will become a negative number for sure, but when squared, minus into minus is going to become plus. As such, it will always be a positive number, and the minimum that you can get out of this is 0. That is when the value of x is minus 1 upon 2. So Even for such a case, we have 0 plus a positive number, which for sure is going to become a positive number and thus can never be equal to 0, right? And as such, you can say that as the denominator is never going to become to be equal to 0, therefore you can say that the domain of the function is actually defined on the whole of real numbers, and there is no real number which is going to defy this. As such, for every real number, correspondingly you will get some of the other value from the codomain. Okay, so this is all that I had for you people in this lecture. I hope you have enjoyed this lecture, understood how to find out the domain of a function. Obviously there are other nuances for which there are other lectures to which obviously I will invite you, as there is a whole compendium of lectures which are the topics which are related with this. That is, first you start off with sets, then you do relations, and then you do functions, and then we have those special type of proofs for functions, like how to prove functions to be injective, then surjective, then bijective. Then we talk about the inverse functions, we talk about binary operations, composite functions, and a lot more. So all of those are there as a compendium. Obviously you can go over and look it up. The link of it I'm going to provide to you in the description. In the description, children, there is another thing which I'm going to help you with. This is a Google form link where you require to write what your problem is, and then I am going to write back to you and I will help you out with the resources that I have and ensure that your problem is solved. Moreover, do look up the description, because there will be essential links for help so that you can do maths with ease. Bye children. This is Saurabh Kumar Dutt signing off, and make sure that you make your maths strong. Bye.